Hello, and welcome to the next part of section 9.7. We're going to talk about, in this video, solving logarithmic equations. Now, for logarithmic equations, you're going to be using the definition of log and some of the properties that we've talked about earlier in the chapter. So I want to do several examples here. Let's start with a fairly straightforward example. Let's say we want to solve the equation log base 2 of x plus 2 is equal to 4. Now we want to figure out what does x need to be in order to make this a true statement. So remember when we solved exponential equations, we use logarithms to help us with that. So it would make sense, since we're dealing with a logarithm, maybe putting it in exponential form would help us here. So what we're going to do is we're going to use our definition of log to be able to rewrite this. So using the definition, we have a base of 2 raised to the 4th power has to equal x plus 2. And now we have a pretty straightforward equation that we should be able to solve. 2 to the 4th is 16, which is equal to x plus 2. And if I subtract 2 from both sides, I end up with x equaling 14. And I have my solution. Now, one of the things that you will want to double check when you are solving logarithmic equations is to make sure that the answer you come up with is in the domain for the log equation. So remember, we can't take the log of a negative number, so we want to check, does this answer make the argument 0 or less than 0? Since 14 plus 2 is 16, I can take the log of 16, so this answer does work. And we are done with that particular problem. All right, let's try another one here. Suppose I want to solve log base 3 of 7 plus log base 3 of x is equal to 1. Now, unlike the previous example, notice that this equation has 2 logs in it. So one of your first strategies is going to be to always try to rewrite the equation in terms of 1 log. Because once you have 1 log, then you can actually use the definition like we did up above here. So in order to write this as a single log, I can use the product property that we talked about, and I can rewrite this as log base 3 of 7 times x is equal to 1. Now that I have a single log, I can once again use the definition. And I have 3, again the base raised to the exponent, log always equals an exponent, is equal to 7x. And if I solve 3 is equal to 7x, divide both sides by 7, and we end up with x equaling 3 over 7. Now again, before I'm convinced that that is the answer, I want to go back up here and check, would this make my log less than 0 or 0? 3/7 is positive, so it does work. What happens is when we do end up rewriting our equations using the properties or the definition, it is sometimes possible to create an extraneous solutions, and you have dealt with those before, so that's why you always need to make sure that it works. All right, so that one used the product property to combine the 2 logs into a single log. Let's try another one here. Suppose I have log base 4 of 12, and I want to subtract log base 4 of x, and that's going to equal 3. Whoops, let's move that up there so you can actually see the problem. All right, well now notice that I have subtraction here. Again, I have 2 logs like I did in the previous problem, but I have subtraction this time. So now I'm going to use the quotient property, which says when I'm combining two logs, I can get log base 4, but now it's the arguments divided instead of multiplied together as in the previous example. So I get log base 4 of 12 over x is equal to 3. Now again, apply the definition of log. We get the base of 4 raised to the exponent 3 is equal to 12 over x. All right, well, 4 cubed, what's that going to be? That's actually 64. So now I have 64 is equal to 12 over x. And it's kind of not very nice that I have that variable in the denominator. So let's bring that out of the denominator by multiplying both sides by x. So now I have 64x is equal to 12, and if I divide both sides by 64, we end up with x is equal to, and 12 over 64 does reduce down to 3 over 16, or if you want to write it as a decimal, it's 0.1875. And so again, both of those would give you exact answers. Now, before I leave this problem, is this answer actually going to work? Well, let's go back up to the original where we have log base 4 of 12. Now, if I were to plug in 3/16 into x, can I take log base 4 of 3/16? Yes, I can. So this one also works. So at this point, you might be thinking, well, wait a minute, all the answers seem to work. Well, let's try another example or two and see what might happen in one of these problems. So let me get a fresh sheet of paper here. And let's try the following problem. Suppose we have log of the quantity x minus 1 minus log of x is equal to 1. Now there's another nice log equation. Now again, notice we have the subtraction, so we apply the quotient rule, which says I have log of x minus 1 over x is equal to 1. All right, so I do need to use the definition of log here, but wait a minute, what's my base? Oh yeah, I do need to remember that log is the same as log base 10. So again, if it's helpful for you to do this, you can certainly go in here and put log base 10 if that makes it a little bit easier to now apply the definition. Because when I apply the definition, I get 10 to the first is equal to x minus 1 over x. Again, 10 to the first is just 10, and I get 10 over x is equal to x minus 1 over x. Notice we have a similar situation as in the last problem. So let's multiply both sides by x. Again, that does eliminate your x on the right-hand side, so you're left with an x minus 1. On the left-hand side, I now have 10x. So how do I solve that? Well, let's put the x's on one side of the equation. So I subtract x from both sides, and I get 9x is equal to negative 1. Okay, solve for x, divide both sides by 9, and I get x is equal to negative 1/9. So is that my solution? Well, wait a minute. If I come up here and plug it in for x here, I get negative 1/9 minus 1. Well, that's going to be a negative value right here. I can't take the log of a negative. So as soon as I see that it doesn't work in either one of these, and actually it's not going to work in either one here, but as long as it doesn't work in one, then this cannot be a solution. This does not check. And so in the end, your answer here ends up being no solution, which again, we can use that symbol to represent no solution. So no value will make this equation true. So just like linear equations, that can happen with log equations as well. All right, let's try one more. Suppose that I have 3 natural log of x is equal to 9. Now again, this is a log equation, but you might notice the notation for natural log looks a little bit different than what you're used to seeing in the previous problems. Now the first thing we want to do is again get the log by itself. Now in this case I don't need to combine logs. I just want to start by dividing both sides by 3 to get the log by itself. I can't use the definition unless I have log of something equaling something. So natural log of x is equal to 3. Okay, now how do I apply my definition to this? Well, if it's a little tricky to view this as natural log of x, you can always choose to rewrite this as log base e of x is equal to 3. Again, that is exactly the same thing. Remember that natural log is a shortcut for writing log base e. But if you're still getting comfortable with that notation, feel free to rewrite it as log base e. Now I can use my definition, and notice I have a base of e cubed is equal to x. And that would be my exact answer here. If I wanted to get the approximate answer, then I could just go ahead and plug that into the calculator. But for right now, I'm going to leave that in exact form. So there are some examples of solving log equations.